Hey Chem team, welcome to our first video feed for this closure. Hopefully this will be a pretty short video series, but I'm gonna do one of these every 3 days to go over a new lesson that we would have done in class, and hopefully it helps you get a little bit more insight into what we're talking about than just looking over the slides themselves, because I know that that's not always the most helpful thing for everyone. So today we're looking at our next standard, which would have been 3.7 valence electrons. I'm just going to go to our presentation mode here. Give it a sec. Okay, if this isn't working, I'll just stay in the... Yep, it's fine. Okay, I'm just going to stay in the editing mode because the presentation mode doesn't seem to want to be compatible with my video recording tool that I'm using. So today we're talking about the number of valence electrons within an atom. Now before we get to talking about how many valence electrons there are, I want you to take a second, watch this video. It's going to talk about periodicity, and I'm going to do this a few times where I will put in a spot in this video or in future videos where I just want you to do something, and it's probably going to be either answer on your own or watch something, and you can just pause the video here. I'll just give you a few seconds and take a look at this. Okay, the main point of the video when they go through is that they're talking about periodicity, which means reoccurring trends of properties within the periodic table. So if we are to look at a periodic table, we would see reoccurring trends within elements that have these similar properties. So things like lithium, sodium, potassium, they all share the same properties, and scientists were like, we know that they do share the same properties, but we're not sure why. So they're talking about periodicity. And Mendeleev, the man who designed our current periodic table, was really focused on the periodicity. So what I want you to do for a second here is to write the electron configuration for sodium, and then write the electron configuration for potassium. And we need to focus on what they have in common. So I'll give you a second here to do that. Okay, I'm going to go over, I have a drawing tool, and I'm going to write out I'll do it along with you here. Electron configuration for sodium and potassium. So sodium, we're looking at 1s2, 2s2, 2p6, 3s, 1, right? Element number 11. Now, if we look at potassium, we see 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, you've probably noticed it when you did yours, but the thing that we're looking at that is the same is this last electron here, right? In the highest energy level, we have 1 electron in sodium. In the highest energy level here, energy level 4, we have 1 electron. Both of these have 1 electron. If we look in the same column, I'm going to try out lithium. I'll give you a second here to try out lithium. Now lithium is 1s2, 2s1. Again, this shares the same style of electron configuration, where we have one electron in that highest energy level. So what we're looking at here, I'm going to switch back over to our slides, is that these elements that are in the same columns, and we call them groups, they share similar properties because they have a similar number of electrons in that highest energy level. So that periodicity, those reoccurring properties of elements, are determined by how many electrons they have in their highest energy level. And we call these valence electrons. If you want to get this down in your notes, valence electrons, the electrons of the outermost shell of electrons, those electrons that have the highest energy. Now, we talked about noble gases before. They're this group here, group 18 on the very far right-hand side. Noble gases represent the completion of an electron shell. And if you think about it, we go 1s2, right? And helium is the final placement of that 1s orbital, energy level 1. Then we have 2s2, 2p6. Neon is the end of 2p6, which is the end of all electrons in energy level 2. Okay? Or we have 3s2, 3p6. Argon is the end of energy level 3. So the noble gases represent the end of that energy level. And that's because of something called ionization energy. So the ionization energy, and we'll talk about this more in 3.9 and especially next unit as well, in unit 4. But ionization energy is the energy needed to ionize an atom. So you either take away or add an electron and it changes the charge, which turns it into an ion. It's no longer an atom. Noble gases are stable gases and they're non-reactive because they have this high ionization energy. It requires so much energy to change the number of electrons that these elements are stable. So it's super, super hard to make them unstable. And thus, we say that they represent the full electron shell because these are the most stable elements that we have. So try this for me. Look at calcium and figure out how many valence electrons calcium has. Okay, what I'm hoping you did, right, is you looked at the periodic table and you wrote out the electron configuration. So you went through, okay, all the way to calcium, 1s, 2s, 2p, or 3s, 3p. Calcium is 4s2 here. And I'm going to write it out with you. So I just need to erase all of this really quick. And I'm sorry, this is taking a long time. I will try to get it all here so we can clear this up. Okay, I'm going to go back over here, allow me to draw again. All right, calcium, we said 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What we're going to look at is the highest energy level. So which one of these is the highest energy level? If you're saying Energy level 4, you're correct, because this is energy level 1, energy level 2, energy level 3, energy level 4 is the highest. So we're looking at how many total electrons there are in energy level 4, and we have 2 of them. So calcium has 2 valence electrons. Now, there's kind of a cheat for this as well, because you can look at the group number up top here on any of the periodic tables, and that is how many electrons, valence electrons, that we should have. So calcium, we said, has 2 valence electrons. It's in group 2. This is offset a little bit by D block when we get over to P block, but P block, it's just the group number minus 10. So if we look at something like nitrogen, okay, it would be, it would have 5 valence electrons, right? It'd be 2s2, 2p3, which means 2s2 plus the 2p3 is a total of 5 electrons, and it is in group 15. So 15 minus 10, that's 5 valence electrons. So that's just a little trick for you so that you can quickly look at that. How many valence electrons does oxygen have? Try this one out for me. Okay, again, you can look at the periodic table really quickly, and you can see we have 16 as the group number, so we should have 6 for oxygen, but we're going to try it out here really quick. So we have oxygen is 1s2, my 2 is a little funky, 2p2, oops, I messed that up. We need 2s first, don't we? 2s2, 2p4 for oxygen. Now the highest energy level is energy level 2, and the number of electrons that we are looking at is all of the electrons in the highest energy level, all the electrons in energy level 2. So 2 plus 4 should be 6. And that agrees here with what we said. 16 minus 10 is 6. Oxygen has 6 valence electrons. All right, as final practice for you before you get into that work that I posted, here's what I want you to go through and list how many valence electrons do each of the following have. And I'll pause the video here, give you a sec. Okay, so you should come back and you should say lithium has 1, aluminum has 3, chlorine has 7, carbon has 4, potassium right here has 1, silicon has 4, and neon, being the noble gas, has that completed shell, it has 8. All right, that's it for this one. Ignore the build a house thing. That was an assignment that we were going to do in class, and then we'd be moving on here to 3.9. So I hope this was helpful. Send me some emails, okay, if there's something that you'd like me to change in like this format. But this is what I'm planning to do for our future standards. Okay, I'll see you in the next video.